This is a May, June 2022, variant 41 question, number 10. Part A carries 1 mark. They ask you what is Wein displacement law. Wein displacement law states that the wavelength of maximum intensity is inversely proportional to the thermodynamic temperature. The wavelength of maximum intensity is represented by lambda max here. So for Wein displacement law, lambda max is inversely proportional to temperature. So lambda max times temperature is equals to a constant. Lambda max represents the wavelength of maximum intensity. The wavelength of maximum intensity is also known as the peak wavelength. The peak wavelength is a wavelength where the rate of emission is maximum. For star A, this occurs at the wavelength of 0.5 micrometer, which is 500 nanometer. Now, how about the peak wavelength for star B? In order to answer this question, you must understand how much is represented by 10 squares horizontally. Now, 1 square is the blue one. So 10 square represents 0.5. So 1 blue square represents 1 over 10 times 0.5. Now, since the lambda max for star B occurs 3 squares to the right of 0.5, you see there's 3 squares here. The lambda max for star B will be 0.5 plus 0.05 times 3, which will give you 0.65 micrometer, which is same as 650 nanometer. Therefore, for star B, the peak wavelength is 0.65 micrometer. Then we know that the surface temperature of star A is 5,800 Kelvin. Determine the surface temperature of star B. We let the surface temperature of star B be TB. So to do this question, which carries 2 marks, we write down 2 equations. For star A, 0.5 times 10 minus 6 times 5,800 equals to a constant. That's equation number 1. Then for star B, 0.65 times 10 minus 6 is a peak wavelength for star B times TB equals to a same constant. That's equation number 2. Then equating the 2 equations will give you 0.5 times 5,800 equals to 0.65 times TB. The 10 minus 6 will cancel off. So that's why there's no need to write 10 minus 6. So from here, your TB equals to 4,500 Kelvin. Part 2. Star B appears less bright than star A when viewed from the Earth. Use figure 10.1 to suggest with the reason. How else the physical appearance of star B compares with that of star A? The emphasis is on physical appearance. To answer this question, which carry 2 marks, you need to know that the wavelength for violet light is 400 nanometer. The wavelength for red light is 700 nanometer. And we know that for star A, the peak wavelength occurs at 500 nanometer. And then for star B, it occurs at 650 nanometer. So therefore, we can say that star B has a greater peak or average wavelength. 650 is larger than 500. Therefore, star B appears to be redder because it's moving towards the red side, which is the wavelength for the red electromagnetic wave is 100 nanometer. Then part C, the lines in 10.1 have been corrected for redshift. You must understand what is redshift and blueshift. Redshift means the wavelength is larger than expected. And then blueshift means the wavelength is smaller than expected. So then part 1, state what is meant by redshift. Redshift means that the apparent wavelength is greater than, or the wavelength is greater than the known value. Known value refers to the values of the same line on Earth due to the movement of star away from the observer. This is how you carry 2 marks. The first mark is for apparent wavelength is larger, and then the second mark is due to the movement of star away from the observer. Then for part 2, Explain how cosmologists are able to determine that light from a distant star has undergone redshift. This question carries again 2 marks. In order to get the 2 marks, you must first say, we examine the lines in the emission spectrum of light from the star, and then comparing it with known spectrum. The known spectrum is done on Earth. This is a summary of the facts that you need to know to solve this question. Number 1, you must be able to recall and use Wien displacement law to estimate the surface temperature of a star. Then number 2, you must also be familiar with Doppler effect and understand the meaning of redshift. Then number 3, and finally, you must understand that the lines in the emission spectra from a distant object show an increase in wavelength from their known values done on the Earth.